Okay. Have you rewatched the recording? Was I audible? Did you watch the recording by any chance? Was the sound good? Was I understandable? Am I loud enough? I have gotten comments that I'm not speaking loud enough, and that's kind of a chronic problem of mine. So let me know if I don't. I'll do better. So today we continue into visual displays of data. Discussion topic number 3 has posted. Please pay attention that next week on Monday, we're going to do our first quiz, which will contain all the modules we have done so far up until central tendency. There's just a quick recap. It's nothing dramatically. It's open notes. You have to practice quizzes to test your own knowledge and your own understanding. The questions are, so the practice quizzes are on randomized sample from the overall pool of questions. Actually, that's that test bank that I'm using. They are basically taking this random sample, so they have their own randomization algorithms. I give them according to the subtopics and the respective question style. So there should be an actual good representation of how the questions are formed and phrased and expressed. It shouldn't be terrible, but you will need to think about the questions. So they are not easy and straightforward. It will require some thought processes. You will have 20 minutes and it's 2 minutes a question. That's what I'm assigning per question. Yes. Well, it's multiple choice, fill in the blanks. There are some short essay questions where you will need to give your own statement. I'm reviewing this myself and I'm quite lenient on it. I'm not going to hold you accountable for every word in there, but basically I want to hear in your own words, what your thoughts are on the question. So it will be something that requires some understanding. I've actually now, in contrast to earlier classes, I have added more short essay questions because it's a more accurate reflection of your actual understanding of the topics. Yeah. Yes. Yes, you can look over it again. Well, you mean with the practice quizzes? Or? Well, that's like a quiz, right? So we're doing this as a quiz. You will have access to this quiz that you have taken, and it will be at your disposition. As said, I have a pool of questions, and the questions each of you gets, each of you will have a different exam or a quiz. It's a quiz, actually.
I think he's asking, like, if you can go back to a question on a quiz, like once you click next, are you able to go back if you want to?
It will, yeah, good point. So as opposed to the practice quizzes, the actual quiz is structured differently. We'll see all the questions at once. So I'm making it a little easier for the actual quiz, so you will have time to go back, think about it again. Makes it easier in terms of time. The practice quizzes are just meant to kind of stimulate the thought process and self-test yourself. So that's why they are a little harder in that regard. It's 10 questions, 20 minutes, yes. It is a mixture of all. It's randomly assembled, so each of you has the same chance to get 2 short essay questions versus 1. So it's randomized, which I deem to be most, how should I say, most fair in the end of the day. Oh, yeah. Yeah, the practice quizzes in the modules. So every module will have a practice quiz. Wrong, not every module, every chapter in Nolan and Heinzen will have a practice quiz in the respective module. We have been discussing it, and you can practice your own understanding with these practice quizzes. Yeah. Yes. Well, the practice quizzes are not enough. So you will need to read the respective chapter. You will need to, I suggest you go through the recording again, because I will outline and emphasize what I think is most likely to be in the exam. And you will need to understand the subject matter. So just doing the practice quiz alone, I don't recommend it. You may be lucky, but I wouldn't recommend.
Okay, for the discussion topics, for the third one, when I looked at it, is there a question in the discussion topic?
Well, if there's no question, I just want you to generally comment on it, what your thoughts are. were in your life you exposed to the topic, or where you think there are parallels from your own life. Just surprise me, be creative, give me an innovative thought, give me something that kind of addressed you in the topic. Yeah. And the discussion topics, I just want to see that you understood what the topic was about and why I thought it was relevant when I included it. Some are more interesting, some are less interesting. I think discussion topic 3 was Hans Rosling, I believe, and he's just phenomenal. So I think you're going to enjoy that talk. He's a very charismatic, very interesting. I think he's from Sweden, from Karolinska, epidemiologist, and he presents data in a very nice, interesting format. I also recommend his TED Talks. I don't know who of you watches TED Talks. It's very fascinating talks of all different topics in life, not only science related. They really cover a wide spectrum, and these talks are really fabulous. And you find Hans Rosling in these talks as well. So yeah. Okay. Any other questions concerning the quiz? Don't stress too much. It's just it means to kind of give you a hint and an idea how the midterm and final is going to be, what essentially is being asked from you. Good. Then on Wednesday, also homework 1 is going to post. That's due on the 15th of February. Kind of schedule your time accordingly and make sure that you beat the time in an adequate fashion. Don't wait until the last minute. It will require a little bit of work from you, but I want to see that you're kind of following along with the Excel practices, and it will require you to do some Excel. But they're not terribly hard. So it's never been a major problem. Well, it involves a little bit of work, so there were some complaints, but it's not super hard. So it's not terrible. But Excel is fun, and I think it gives you a good head start into how to operate Excel, how to use the functions in Excel. Any other questions? If not, then let's get started. Not this. This now. Okay. So visual displays of data. So visual display of data, I kind of gave you an idea why it's important. You really want to communicate your data. You want to do it in a tabular form by doing frequency tables, as we've done last class. We do frequency tables and grouped frequency tables. We talked about histograms and dot plots, which allow you to understand the frequency distribution of certain values. And you can do more with data. You can do more visual displays showing your data. And so the pool of ideas is virtually limitless. So there's very fancy methods that are being done. It's getting increasingly popular to also do 3-dimensional graphs. You can even create 3-dimensional graphs that you can actually, like a GIF, turn around, and you can kind of look at the data from different angles. So there's really a lot of innovative stuff out there nowadays. But basically, we're going to be focusing on the more classical forms of depicting data. And we will particularly talk about the positive and negative uses. So why is that important to understand positive and negative uses? Because unfortunately, it's used in a positive and negative way. And in addition to that, if you read a paper, the only thing you basically see is a table and a graph. And then you have some wording that basically describes table and graph. What you want to see when you want to understand and intellectually penetrate this topic and the research question asked and how the author's meant to answer it, you need to kind of find your own interpretation of tables, graphs, and the text. Because sometimes the interpretation is not necessarily really what you're seeing. So it could be that that interpretation of the text is basically not as accurate, or the authors missed something, or they're misinterpreting something. That's why it's important that you build your own opinion about what you see and what you read. And that's kind of what I think this class should be inducing for you, this thought process of question everything that you read, and not just take the text and take it as it was written, but really question it and look at the graphs, look at the data, and build your own opinion about it. So as said here, graphs are meant to accurately and succinctly present information. So they're actually very much packed with information, and they would allow for you to understand this data in much detail. It can, in addition, it can reveal and conceal complicated data. So it actually can give you insights that sometimes a table does not provide to you. A graph may provide this. And we will see graphs like, for example, a scatter plot that actually gives you an idea not only about the distribution, it gives you information about each individual data point in your data set or in the data set of those authors. So it really gives you an idea about outliers, about skewness. It gives you all kinds of information. So there are very sophisticated approaches to visually display data. So this is a convincing graph, but to be honest, it's also a little bit of a tough graph. This is a so-called cock-comb graph. So the comb of a cock that basically shows different pies of a certain fraction. So what is now being shown, you have this very same cock-comb graph, as each of these slices represents a month of the year. What's interesting in this, that it displays the count of deaths. In addition, it also displays the proportion of deaths. So this, we're talking about the 19th century, and there was one particular year that is depicted here. It was developed by Florence Nightingale and is counted as one of the early ways of depicting very sophisticated data in a very sophisticated manner. So you have increases in the deaths, in the numbers of deaths. You have increases in deaths from different causes, and this basically changes with violent conflicts, resulting in a greater fraction of those that died from wounds in battle. And then you saw the battle subsiding, so the number of wounds from battle basically decreasing. But what's increasing now is the cause from the deaths from other causes, which coincided here with winter. So after a war, resources are depleted, people are more likely to get sick. So you see an increase of the other causes of death. And then in addition to that, deaths from disease, which is also coinciding then with the season of the year. So this is a different way of showing a time series, essentially, where you have different months shown as a line graph, which we'll see later. It's just one way to present percentual data of deaths from certain causes, and with the aim to use this descriptive statistics to draw inferences. We remember descriptive statistics lead to inferences, and then inferential statistics allows for hypothesis testing. That was the first chapter. Good. So any questions to this graph? It's quite a sophisticated, quite advanced graph, but it basically, it gives a signal in terms of how the causes of death shifted and how the death count basically shifted, given the prevalence of different causes. Then in addition to that, you also have the problem that many graphs are misleading. And Norton and Heinzen showed this graph as the most misleading graph in the history of publishing, which I'm not sure it's the most misleading graph, but it's definitely a very problematic graph, because there are various things that are basically going wrong. So I don't know, you can see it in the projector, but basically the starting years are entirely different. So basically this overlaid time series is wrong. So it basically starts with a different year for both graphs. So what it means to show is the cost of a tuition at the university and the ranking of the university. So firstly, there are wrong time periods. That's where the conversation starts basically, and renders this graph absolutely useless, because the most important thing with a time series plot is that you start at the same year and you end at the same years. Otherwise, the graph is not interpretable and not really valid. Secondly, you have two different scales. So if you have a tuition, that is obviously continuous data. This is ratio data that basically will be depicted as a time series. Whereas the ranking of a university, by definition, needs to be considered ordinal data. So if you have a ranking for a certain for a university in the global or in the national ranking, this will be ordinal data, and these two data cannot be combined and cannot be looked at in this shape or form. Secondly, you have a y-axis and an x-axis. So if you have a y-axis and an x-axis, you need to understand what your y-axis and your x-axis is. So your x-axis here is time, which we have learned in the first point is different time periods. So the x-axis is shifted and not correct. Secondly, the y-axis, you don't have a starting point. You don't even know what is being depicted here. Secondly, more importantly, is like you don't know where it actually starts. You don't know what actually the reflection of this ranking is, and you don't know what the tuition is. So it just means to mislead, but just show something that nobody really understands. Lastly, and that's the most bizarre aspect of it, you have a reversal of implied meaning of up and down. Because logically, when you have a tuition cost, more expensive tuition is not necessarily a good thing, right? But the ranking of university, if that is a lower value and it actually gets to spot 1, to rank 1, is actually a good thing. So I don't know what drove them to depict that data like that, but it's a rubbish graph at the end of the day. So this is the take-home message from this graph. So this already indicates all the different things that you need to keep in mind. You need to look at the graph. You need to understand what data are you looking at in reference to what values. What do all different dimensions of that graph imply and show? Understand the x-axis, understand the y-axis, understand the x-axis, and really know what you're looking at. Understand what the interpretation of these numbers are and what you can interpret safely from the graph without making misinterpretation. So there are various lies with graph. You have a biased scale lie, which we're seeing here basically. So you use scaling and different scaling approaches to basically conceal the true meaning of your data. So you use 3 different words out of 5 options is what Nolan and Heinzen state here. Then there's a reversal of the meaning of up and down. So these are different ways how the scale will basically mislead. And we will see a couple of examples later. And just a couple of slides later, we will see more examples of that kind. Then you have a sneaky sample lie. So the sneaky sample, I've never heard that term before I read the Nolan and Heinzen book. Sneaky sample implies essentially what would be considered, well, it's kind of a selection bias, an implied selection bias that you're picking only data points that actually corroborate your interpretation of that graph and what you want to show to your audience, which obviously, for obvious reasons, this is a big no-no and you cannot do that. Secondly, you have an interpolation lie. So you have an interpolation lie and extrapolation lie. And so inter and extra. Inter means in between, extra means outside. So when you have a time series plot and you have data depicted as a function of time, so you have any data, any variable on the y-axis and you have time on the x-axis. Let's assume this is the easiest example. You're having one data point of one time point and you have a second data point of a second time point. Let's say we have, and there's an example for that. Let's do it with an example, it's easier. So these are visual examples for an interpolation lie and an extrapolation lie. So an interpolation lie would be that I say between 1986 and 2006, there was a decrease in crime rates, which is formally true. If I only take 1986 and I look 20 years later, 2006, there was a decrease, right? Slight decrease. But I'm not paying attention to what happened in between. That crime rates actually spiked sometimes in the mid-90s. And that's obviously something that you should not be doing because that conceals the information to the reader that there was actually a spike, that prompted, I don't know, more police presence or whatever they did to curb the crime rates, and then the crime went down. So this is an interpolation lie. You connect two dots and you say everything was in between is irrelevant. That would be an interpolation lie. So that's why it's important to always show the data at the highest granularity that you have at your disposition, because you want to make this an accurate reflection of what really happened with your data over time. Second, here we have, okay, let's go back to an extrapolation line. An extrapolation line, so inter is in between 2 points. An extrapolation line would be, I'm seeing a decrease in the crime rate from 1998 to 2006. Thereby, I project, or I assume the crime rates need to decrease or will further decrease. So you're extrapolating beyond that data points that you actually have at your disposition based on the trend that you're seeing. So this extrapolation also cannot be done and should not be done. So it's a purely hypothetical trajectory you're seeing, and you cannot assume with much certainty that it will really continue to decrease. You could speculate, you could build probabilistic models that allow you to kind of give that estimate with a certain level of certainty and confidence, but you cannot really make any solid conclusion based on data and based on assumptions of data that you have beyond the data that you actually have at your disposition. We have then on the right side, we have a biased scale lie where we basically have the y-axis distorted. Why is that problematic? So when you look at these different bars, well, first of all, never depict data in such a pictorial format. And we will see another example later on why pictorial depiction is problematic. But when you look at the way this data is presented, it gives a visual impression that whatever happened here before, so there was recruitment of nurses, was actually so low and it was virtually inexistent. However, then in 2011 and 12 and 12 and 13, it was just, they recruited so many more nurses. And this is particular, to be honest, it's like in scientific papers, you will not see a graph like that. You will see this more in like magazines, newspapers. Newspapers are always look with a great level of cautiousness at graphs in newspapers and magazines. So scientific articles would not show this. But yeah, it's distorting the scale. It basically makes a certain time period here more prominent and stronger with the aim to distort the interpretation of that graph in a certain shape or form. So just the reason why they're showing this graph is like, just pay attention, understand what you're looking at, understand what the scale is, and pay attention to it. A graph that I personally like very much is the so-called scatter plot. The reason why I like it is because it allows to see every single data point. Seeing every single data point is sometimes hard, particularly when there's a lot of data. If you have data of 100,000 patients, that scatter is basically, it's a cloud, and you can't really interpret anything from a specific data point. So there is a graph for each individual use case, so keep that in mind. Scatter plots are really good if you have like a mid-size sample that you're looking at, then it's very useful. The beauty of a scatter plot is that it allows for you to look at the relationship between two different variables. And what does that mean? Yeah. And I want to show you that it's examples. So we have here athletic performance as a function of hours of exercise or deliberative practice. So keeping this in mind is like if you practice a sport and you put the hours in to practice the sport correctly, the more hours you will put in, the better your performance will get. I guess that's quite logically. And so what you see here is what is called a positive relationship. So you see an association that is positive in nature. That means more hours, better performance. This can also be the other way around. It can be an inverse relationship or a negative relationship. That means the more of X, the less of Y. So it can go in both directions. This is a positive relationship, and it allows for you to understand what that relationship looks like. And if you have every data point at your disposition, you can do two things. So there are basically two relationships that you may see, whether it's positive or negative, irrespective of the direction. It allows for you to see linear relationships and non-linear relationships. So linear relationships are quite logical, right? So this is basically you can draw a line through, and this trend will basically be quite consistent for all the data points. Whereas a non-linear relationship is something that takes a certain shape. So you may have heard in high school about the shape of an exponential increase, a logarithmic increase. And so there are different ways how this can be different shapes, can be cubic increases. So there are various different shapes and forms these nonlinear relationships may take on. This would be most likely, if you had more data, you could establish a linear relationship with this data. So now the question is, how do you create such a scatter plot? And this will be important for the homework because you're asked to create a scatter plot for this data. So firstly, what you want to do, you organize the data by participant. It's again important, just like with the Stroop test, that each individual data point, both on the first variable and the second variable, is aligned. So don't shift the order for the variables. So you only use this aligned pairs of data. You label a horizontal x-axis with the independent variable names, possible values. You label the vertical y-axis, and then you mark the marks on the graph and put it participants score on both axes. So it's simple, right? So you have one value. So each of these points is one individual subject, one individual student, or athlete. So this is one individual, and you have an x value and you have a y value. So you basically you go on the x-axis, you find that respective value, you go straight up 90 degrees angle, and you find the corresponding y value, and that allows you to draw that one point. Simple. This is if you would do it by hand. I don't discourage you to do it by hand. If you want to do the homework by hand, please feel free to do so. Send me a snapshot of your work and I happily look at it. What I would think is more reasonable in 2023 is to do this in Excel. And Excel allows for you to do this quite simply by basically taking this data and organizing it as per X and Y. So we have the first column on the left is your X. That is, and it's on your module. The spreadsheet is on your module. So you have in column A, you have the hours of practice put into that particular sport. On the second column, on column B, you have the athletic performance. One thing you have to pay attention to in Excel is that the first column to the left will always be considered the x-axis by default. And I don't want to go into the details because then you would need to switch the axis, then things get a little messy. If you can organize your data in that format that you have on the x-axis, that you have the first column defined as the x-axis, and the second column the y-axis, it makes it easier for you to compute that graph. And in the end of the day, what you want to do, you select then A1 to B21. You click on Insert, and you are now clicking here on Graphs, which is somewhere here, depending on the OS you're on. And the only thing you need to do, you need to find that graph that shows here X, Y scatter. I don't know whether you can see that, but it says here XY scatter. And once you hover over that, you just need to click it. And then you basically get a different selection of the scatter plots that you want to show. So if you're clicking on the first one, which is the most reasonable one, you get the same graph shown as Noren and Heinz now showing.
What's it called? That's why.
XY scalar. It should present.
I see different options for scatter, but I don't see like all that.
So if you open insert, you just go a little to the right. There should be like a collection of different graphs.
Yeah.
So they are the bar graphs, which look like that. You have combo, waterfall, hierarchy, column, pie. Somewhere there should be XY scalar. It really depends on the version you're on. Yeah.
I accessed it like through like YU, and on Excel, like it shows scatter, but it's scatter with only markers where you compare pairs of values.
Okay, yeah, this is paired values.
Okay.
So if you're just selecting A and B, I think hypothetically you could even be able to click on recommended charts. On recommended charts, you get this selection. It's also the scatter plot would be the first one. As said, it's one of the most popular graphs that you have in your toolbox. So you can change the title of the graph by basically showing athletic performance as a function of hours of practice. So that's where you would adapt the actual title. You can then, if you click on the graph, you have then here on the right, you have chart design and format. If you click on chart design, you get here on the left, add chart element. An add chart element, you can, if you click that down, it allows you to label the axis, give axis titles, chart titles. You can do various things that you basically can modify on those graphs. So if you click now, yes. Yes, absolutely. Thanks for reminding me. Better? Okay, good. Okay. So if you click here on add chart element, you can customize your axis title. So if you go on primary horizontal, you can modify now primary horizontal. Let me zoom in a bit. So here you do hours of practice. So that's properly labeling. Second thing that's important, whenever you label, bless you, whenever you label an x-axis, you always need to state the actual unit. So if you have hours of deliberative practice, the unit is hours, right? So that's simple. And commonly, I gravitate towards taking here the parentheses or the brackets. It's actually bracket. The brackets to display the units because that's how it's done in the SI convention. So you write hours and you indicate what the unit is. If you want to label now the y-axis, you go back to add chart element, you go to axis title and you write primary vertically. Primary vertically basically allows you now to change that, and that would be athletic performance. Athletic performance was a unit that we don't know, so we can leave that out. And I'm not even sure what athletic performance could be as a unit. But it doesn't matter. It's just for the sake of the depiction. So now you have all these organized nicely as a scatter plot. You see the various data points. Each individual point is one subject. And now you can do, and I'm stepping ahead a bit, you can also do the following. You go again to add chart element. And there's the very last entry, or the very last not blanked out entry, is add trend line. So with add trend line, you have non-linear, exponential, linear forecast, or moving average. So what do these mean? Linear, we talked about it, that's like fitting a line through. Exponential is the exponential increase. That would be a slight shift, shaped to the lower end, or curved to the lower end of Y curve. Then you have linear forecast that basically will show a forecast that smooths spline. Then you have a moving average that changes with the respective average at that point. It basically means to depict that line. That will be more of a spline function actually. Okay, so if we do a trend line and we choose linear, it will do exactly that. It will fit a linear line through that. So it will, this is the depiction of a linear relationship. If you look at the data point, is it a good reflection of our data? Yeah, not great. It's not great. And I'm stepping ahead a bit. If you double click the line, you just select the line and you double click it. You can here on the right, you can say display equation on chart, and you can show display R squared value on chart. And this is a little bit early for this conversation, but basically all of you have learned in high school how to evaluate and how to calculate slopes and intercepts and how to express a linear function, a line function. This is that line function. So this is basically the slope, that's the intercept. I will talk about that in chapter 16, but I'm just meaning to kind of provoke that thought and memory from your high school education. Then we have an R square, and the R squared is basically a depiction of how well does this line reflect the individual data points. Good. So this is how you do a scatter plot. You will need that for your homework, so please make sure that you know how to do that. Any questions on that? No? Good. Okay, linear relationships, nonlinear relationships, please understand the difference and know how to do those scatter plots. The very characteristic things is that basically it depicts a relationship between two variables. Will become particularly important with chapter 15 and 16. That's correlation and regression analysis. So possible stories from scatter plots, we talked about it, there may be no relationship, then this is basically a flat line. So this line, if you would add a trend line to something that has no relationship whatsoever, it's a flat line. A linear relationship is best described by a straight line. It's also the most common form. It's like nonlinear statistics. That's a whole different animal, and that's a tough cookie. So that's not an easy topic in statistics, and that is definitely a more advanced conversation than the one we're currently having. But yeah, it's basically, if you have a nonlinear function fits best through that, then you would assume this is nonlinear relationships, and then you need to deal with this data entirely different. So you can't use those methods that we're discussing in the course of this course. Good, but it's important that you know what it is, and this is a 100% quiz question. So there's a good chance you will have this question. Just know how to distinguish and what the implications of that is. Good. Line graphs. Any questions to scatter plots as a general topic? It's very fast. Please read also the chapter 9 and 10, that may give more insights. Good. Line graphs is basically a graph that again has individual data points, but the peculiarity of that is that these data points are connected. Do never connect data points in a scatter plot. For that very reason, because in that scatter plot, each individual data point is a different subject. So there is no association. If you want to build line graphs because you have repeated measurements of different individuals, then you may consider a line graph, but then the whole way of depicting this data changes. If you do a scatter plot and you want to see a relationship between two variables, do never connect the dots. So a scatter plot basically means to construct this line of best fit. The line of best fit, just as a quick, and I actually was better on the Excel sheet. So we have here, this is a line of best fit. This is a line of best fit because it's the best fit, and what Excel actually does, it creates a function that minimizes the distance of the individual data point to a possible line that is being fit through. So it takes each data point, it calculates, okay, so how far is that away? And it calculates like what slope and what intercept does my function has to have, that it fits through all the data points as a whole, with creating minimal distance of each individual data point to my potential hypothetical line. That is called the so-called least square approach. I will talk about this again in the course of the class. So the least squares are called the least squares because you take the distance of that data point to the line and you square it, and you want to minimize that squared distance. Yes. There's no relationship. Well, that is an excellent question, and sometimes this is not very clear cut. And this is why you need what is labeled up here as R squared. And that's why I showed you that, because that essentially corroborates that there, in essence, really is a relationship. If this would be a flat line, this R squared would be closer to 0. So this R squared moves from 0 to 1, with 1 being a perfect relationship. So that would be where y equals x. So you move up here and it's exactly the same value. It's like one straight line, all the data points are on that line. That would be an R squared of 1. If you ever see that everywhere, it's like somebody's lying to you, because that doesn't exist in the real world. So but yeah, that would be the metric. So it ranges from 0 to 1, with 0 being a flat line, 1 being like this perfect 45 degrees relationship. So the slope would be 1 in that case. So you basically, the slope would be exactly 45 degrees then. Well, if it's 0, then it's 0, then it's flat line. So it's y as a function of x. So that would be 0 slope, no increase. So that's, but these are the subtleties. These are very advanced questions already. Good questions, but very advanced. We'll talk about that in regression. So yeah, no, but basically you need a metric to depict how good is that line? How good is my model? This is, in essence, this is a function. This is a model, a so-called regression model that is being fit through with a least square approach. And the metric of how useful that model actually is the R square. And so if there's no relationship, that R square is really low, and then you would not do that. Then you would seek alternative approaches, or you would accept that there's just no relationship at all. Good. Line graphs. So the scatter plot is used to construct this line of best fit, as Axel labels it, the trend line. A line graph is used to visualize an y-axis, so changes in the y-axis in values over time. And the most prominent example here is a so-called time series plot. Time series plot because you have the same group of people over time, and you're following this over time, and you show the time series of the y values over time. That's when you use a line graph. So the line of best fit is that. We've just done that in Excel. We know now about that. And that would be a time series plot. So time series plot really shows this as time of the day, different years, whatever involves showing data on the y-axis as a function of time, whatever time metric you're using, is a time series plot. That's how easy it is. This is when you can use a line graph. So this example here is actually quite amusing example. It is mood changes on Twitter as per the hour of the day. So what's interesting, you can see a couple of patterns in there, and this is now where we're looking into the intersection between descriptive statistics and inferential statistics. And that's actually fun. It's like, I don't know, who of you knows Google Analytics? Google Analytics is actually freely publicly accessible Google data on search queries. For example, they show data like where is the closest, it shows the frequency of the search term, where is the closest pharmacy, that increases during the flu season in winter, and it's lowest in summer. Where do I get the best sunscreen? Higher in summer, lower in winter. So they are really fabulous kind of data that Google just puts out for the sake of crowdsourcing, basically making it accessible to the public to see like what data is in there. They actually papers published just based on publicly accessible data on Google. So it's just a fun data. So this is data from Twitter. And so what they mean to reflect is a time plot that shows mood changes on different days of the week, which are here color-coded, and different hours of the day. And what you can see, and that's interesting, when you take here Sunday, for example. So firstly, Sunday is, most people are off on Sundays. That means the positive attitude is considerably higher for everybody. What's even more interesting is if you look at time of the days, like I don't know how long you sleep, but majority of people seem to be waking up at 8, 9-ish, and they realize it's Sunday, I don't have to go to work. The positive attitudes are more likely to be positive and higher. Whereas if it is a Monday or a Tuesday, it increases here slightly when people are waking up. Then they're going to work, it's going lower. Then they're going home from work, and it's getting higher again. So it's just, it's fun to see this data because it's a reflection of what you really see. And so now this is Twitter data, and that's more like, yeah, it's not necessarily too insightful. But a lot of the things I'm doing in my work and that researchers do is you first establish these kind of signals. You see something which you know has to be in your data. Based on that, you basically, know that this data that you have, that data set that you have at your disposition is indeed reflecting what you would expect. And then basically you take the data to answer a specific research question. And that is just a phenomenal example of where you really see real life, real world evidence. And that's, nowadays, this is like everything evolves around real world evidence. And if you look at epidemiology and if you look at job postings anywhere, it's like real world evidence, analysts and real world evidence, these are jobs that are highly rated and just are super popular these days. Yes, please. Well, Sunday at midnight until 3 a.m. You may not be a happy camper. So Sunday at midnight, you basically you come home from going out. I don't know what the underlying metric is or what the reasons could be. But if you tweet on a Sunday or Saturday night, Sunday morning from 12 to 3, not sure how happy you are if you tweet at this time of the day. But that's all speculative, right? I just showed the more logically reasonable. The rest is up for speculation. And I would like to leave it at that. Okay, any more questions about Twitter and time series? So this is a time series plot. Basically, keep in mind everything that's depicted on the x-axis as time, as a function of time. Also, when I say as a function of, so you have seen that line function that I've shown in Excel, which is a y equals xyz multiplied by x plus a number, xyz, which is the intercept. So you have slope plus slope multiplied by an x plus the intercept gives you an estimate of the y. So I will use this, and I'm flagging this, and this is not just me, as every statistician will use the same terminology, will understand the same terminology. If you want to express a relationship between two variables in a scatter plot, and this is a scatter plot, in a modified version, this is a scatter plot because it's negative attitude or positive attitude as a function of time. If you have that scatter plot, it's athletic performance on the y-axis as the outcome dependent variable, which is always on the y-axis, as a function of hours of exercise. That's important. Any questions? Okay. Good. Time series plot. So next, so now we're coming in the realm of categorical data. So we have here a bar graph and a Pareto chart. A bar graph can depict continuous data, but in many cases is being used to show categorical data. So why is it, so it's, if it's scale data and you have nominal data, you would have different graphs. So nominal or ordinal data basically means like this is a category. This is like, let's remember our happiness example. How happy are you on a scale from 1 to 5? You have 100 people, you have 20 saying they're very happy, 40 are not happy at all, 30 are somewhat happy. So you basically, you have different counts for different groupings. So then the count of these respective categories becomes a continuous variable, a scale variable. And this is how you depict it. So you basically, you show the frequency or the count or the percentage. So every scale variable you want to depict as a function of the respective nominal variable. So the nominal variable is here a name, which is here country. Whereas the Y variable, the dependent variable, is here the percentage of internet users who also use Twitter. So this is a standard bar graph. What is this? Oh, this is a standard bar graph, and the height of the bar represents, it's mostly an average value. It could also be a median, but we'll talk about that when we get there next week. No, on Wednesday. But basically the height of this bar shows a value. Not an individual value, but it will show somewhat in that category. And that category can be either a categorical variable to start with, or it can be also bins of a certain value. It can be a group frequency table. We've seen the histogram. A histogram is nothing else but a bar graph with the occurrence of an individual value in that range of data that you have defined as the bin size. So it's basically, it's the same way of depicting the data, and you see this frequency distribution. Yes, please. Okay, no, it's the same thing. A histogram is literally a bar graph showing data or bins of data. A Pareto chart is essentially a bar graph that is ranked. So you basically, you have, so you have here, you have the Twitter users, percentage of internet users who also use Twitter for each of the different countries. The only thing you do for the Pareto chart, you're basically ranking it with either the highest first and then having the ranking accordingly, or you show the lowest first and you have the ranking accordingly to the highest. So that's a Pareto chart. Both are kind of interesting to look at, and the use cases when you use either or really depends on what data do you want to show and how do you want to show it. So it really depends on like what's the message you want to convey to your reader or to your auditorium. So it's simple. So bar graphs highlight differences between averages and percentages. So this is basically, this is a category, and you categorize this data according to the number of tattoos an individual had, and you basically see an increase in the individuals with more tattoos if they have been arrested at least once. So yeah, debatable analysis, but okay. So there seems to be an increase. You can start bulking it differently, and that's the tricky part, right? So you need, and this is the power and importance of categorization and granularity, because the more detailed you present your data, the more insightful your data will become. Because just when you compare this graph versus this graph, you have here a whole different subset, and this is the power of the categorization, because now the extreme category is left out, and you have essentially also a discontinued y-axis. Discontinuing y-axis is the same problem than you had with the recruitment of nurses, where you basically discontinue the y-axis and thereby you lie by deceiving with the scale. So that's problematic by its own right. So what's also important that you need to focus on showing your data in a very clear fashion. You should not try to be overly clever in your, well, clarity is clever. So it's somewhat disagreeing with the statement. But basically what it means is like, stop trying to embellish your graphs. No, so there are various ways of how statistical softwares allow for you to make things prettier. And you can do like all kinds of dots and patterns and whatsoever. It's like, don't do it. It's just plain and simple. You want to show data, make the graph as simple as possible. No different colors. This is usually all unnecessary to use. And so really reduce the number of dimensions that are potentially misleading and distracting the reader from the essential message. And that's just like the most prominent example to do that is like, so this is a so-called pictorial graphs. You basically show city A versus city B. Is like, there's just no reason on planet Earth why that should be depicted that way. And it's misleading, it doesn't make any sense. So second thing in graphing, so you will see quite frequently pie charts. Don't use them. So I do have a little bit of antagonism against pie charts because they're misleading and they're non-informative. When you look at a pie chart like that, you see each pie represents something. But if I ask you now quickly compare reasons why students reasons that parents don't want to learn about their kids, and you basically I ask you to compare about the record of having cello shots, you would not be able to give a quick response for that because it's color coded in a confusing fashion. So this does not allow for direct comparison, and this is not very insightful. It's always more insightful to show exactly the very same data as a bar chart, as a properly depicted bar chart that gives you a much better means to compare individual entries and individual categories to each other. Pie charts are very popular. A lot of people basically use them. You find them in scientific papers. I don't know why, but you find them. You find them in magazines, you find them in newspapers, and they're just utterly terrible. So I highly recommend against the use of pie charts. But the concept is clear, right? It's like, so you have 360 degrees that you can split according to the percentage that you have. 360 divided by 100 makes it 3.6 3.6 degrees for each percent. And then you just take the percentage, you multiply it by 3.6, and that's exactly that fraction of the pie that you need to color in one color that you know the actual value. It's yeah. I can't even stop talking about it. It's just not a good idea to depict data in pie chart. Good. What's really important to keep in mind is that these graphs do have their respective use cases. If you have one scale variable and you're interested in frequencies for respective ranges of your data in intervals, you do depict this as a histogram, or the smoothed linear way of doing that was a frequency polygon. Statistical softwares will allow for you to do either or also do them combined. If you have one scale independent variable and one scale dependent variable, again, dependent variable on the y-axis, independent variable on the x-axis, you do either a scatter plot, or if the independent variable is time, you do a line graph. one nominal or ordinal independent variable and one scale dependent variable, you do a bar graph or a Pareto chart. Depending on the use case, you will either rank them or order them or not. Then you will keep it as bar graph. If you have two or more nominal or ordinal independent variables and one interval dependent variable, you use a bar graph. The reason for that is because then you don't want to regroup it. Because if you have an ordinal variable on the x-axis, you don't want to regroup them according to the number of occurrences. So there's a meaning on the x-axis. That's why you don't regroup it. So how to read a graph? And this comes back to what we have discussed now, right? It's like, so first of all, look at the graph. What are the variables? What is the y-axis? What is the x-axis? What's the dependent? What's the independent variable? Why? And what is the message of the graph? Then you want to understand the nature of the variable that you're looking at. Is it nominal, ordinal, or scale? What are the units of measurement? I talked about this. Always put the units of measurement in the vertical and the horizontal axis title. So it always should be there. There should be no guessing. Absolutely no guessing. Which variables did the researchers use to predict the dependent variable? That is, what are the independent variables? Yeah, we said that before. Are these two independent variables nominal, ordinal, or scale? And what are the levels for each of these independent variables? So if you have a bar graph, just understand what this actually means to reflect. So these are really the critical questions you should ask yourself. Also, I'm flagging this. It's like make yourself familiar with this because there will be graphs for you to interpret on the quiz.
Will we have to create a graph on the quiz, or just
No, not create, not on the quiz. For the homework, yes, but that's you have time to figure that out. You don't have to submit anything. It may just, for some questions, it may be helpful that you have Excel open and you do some calculations in Excel. No, it's so you get the entire quiz in front of you. So you have all the 10 questions, or for the midterms, it's like all the 30 questions. For the final, then all the 35, 40 questions.
Is it on Canvas?
It will be on Canvas, yes. I just want to emphasize it's open notes. That means you can use your notes, you can use the slides, you can use your book if you want to bring it. That's fine, but I will walk around and make sure no messaging, no Google, no whatsoever. So it's open notes. That means use your notes, but don't try to Google the answers. There will not be much success in Googling them anyways. Okay, general guidelines, clear specific title, makes sense. Labeled axis with variable names and units. Compatibility of terms on the graph and in the text. Yeah, so use the same nomenclature. If you call A in the title, it also should be A in the legend and in the axis title. Inclusion of units of measurement, both for the X and the Y axis. Values to 0 or cut marks. The cut marks are debatable. If you can avoid them, please avoid them. If you need them, make clear that this is mentioned on the graph and that you also mention this in the caption. Simple, clear use of colors, and do not employ chart chunk. And that's a specific topic, and that will also be on the exam. Chart chunk. Understand the differences. You have Moiré operations. You have a grid and you have ducks. What is this? So you have here more reverberations are the patterns that you can fill the bars with. Do not use that. The grids is that in the back. If you really want to use a grid and give like a reference line, make it a very wide grid that basically allows just as a reference. And the ducks, that's like additions to the graph that nobody needs. And it's just meant for illustrative purposes. Avoid those. Also, it's sometimes misleading because many of these graphing programs actually do offer a lot of these chart chunk additions. It's definitely important to not resort to the default. If by default you get any pattern in your bar, just take them off. So don't resort to the defaults, but make sure that you're kind of reviewing how your graph looks like and how you think it should be looking like. The future of graphs, and this is where Hans Rosling also comes into play, because he's basically showing this as bubble graphs. So he's doing a lot of bubble graphs, and bubble graphs are brilliant kind of ways of depicting data, and we're seeing one on the next slide after that. But the future of graphs is like the interactive graphing. So I mentioned this, is like you have like a 3D graph, and you can pull and drag, and you can distort them, and you can look at different angles at this data. You can zoom them out. You can take certain parts of the data out. So you are able to manipulate this graph according to what you're interested in. It's fabulous things out there. Then you have computerized mapping, and there's GIS-ARC, ArcGIS, and ArcGIS, ERCGIS. There are various other softwares. There's open source software that allows for you to import maps and fill certain countries with a color and reflect those colors according to World Bank data. So there are fabulous things out there, all open source, all for free, where you have the capability to work with maps. And really do a lot of manipulation and show a lot of your data on a world map, on a county map, on whatever map you're interested in. There's so much information out there, publicly accessible. There's so much maps that you can import in all kinds of different softwares. R allows for a great deal of map creation and coloring. So there's wonderful things out there. Clinical applications, yes, and that's getting more and more popular nowadays. If you have a patient that comes in, you can hypothetically, you can have all the information on a tablet. There are business intelligence tools nowadays where you can have all your graphs displayed. You can again use interactive swiping, and you basically look through the medical history of the evolution of lab parameters over time for a patient when the patient comes to you. So you can see trends over time, and this becomes more and more important also in my world, for example. Then you have word clouds. Word clouds, you must have seen, that's basically like the Wordle. So where you have like different words that come with a certain frequency, that appear with a certain frequency, and those that were most frequently appearing are larger. So there are various ways to look at things. And this is the promised bubble graph. The bubble graph basically informs and shows a lot of data. So you have your positive emotions as a function of self-reported health. You see various countries, the size of the bubble shows the number of inhabitants of that country. The color of this shows the happiness, the reported happiness. That means that small countries with little positive emotions and poor health, like Georgia, although I'm not sure, but Georgia, they're very happy people actually. So Georgia essentially presents with red, small, it's a smaller country, same as Armenia, basically low happiness, low health, low positive emotions. But when you go then up and you have here Ireland, I don't know, healthier people, a lot of positive emotions, larger country, and considerably happy. So this is how you depict this kind of data, and you have several dimensions of data included in your data, in your graph. Yes. This is a bubble graph. Yeah.
And why is it called
happiness? So, and this is a good point, because what the authors, what Nolan and Heinzen have not done here, which is a big no-no, they have not shown you a legend of happiness. So usually whenever you color code something, obvious question is like, what does the color mean? They're not showing this.
So the color is a separate variable.
It's a separate variable. It's two, no, it's actually four. It's the fourth is size of the country, or size and number of inhabitants. So there's a lot of data. That's a very loaded graph. Yes.
Why are there more bubbles than faces?
Well, that's the next problem is like it's not as not every country is represented. So that's the fifth variable actually. That's the fifth variable would actually be name of the country. So the actual label of the category. Good point. Good point. So hypothetically, you should actually see each of these countries. So the only thing it meant to show is this relationship between size, health, positive emotions. I don't know what the meaning was. I didn't look that one up, where the data was coming from. But yeah, there was some study that was conducted in that regard to show that data was probably relating health, positive emotions, and happiness to each other. Hard to say what the underlying research question was. But it's just interesting to show data and this multidimensional data on one graph. And you could hypothesize, you could look this graph up for a long time, and you could do a lot of different relationships that you could see in there. So it's just interesting to show different dimensions on one graph. Then you have uncovering hidden stories by displaying variability. Bar graphs come at the price that you don't see the individual data point. That is a high price to pay, because in a scatter plot, you have each individual data point. With bar graphs, you're parking that together. You don't see the differences from the mean. You don't see that variability. So that's a problem. And then you have, lastly, you have the so-called violin plot. And we'll talk about this part in here on Wednesday. So this is basically the middle score. Below the middle score, you have 50% of the data. Above the middle score, you have 50% of the data. And this here, vertically, is basically a depiction of the frequency distribution of the data. So you have, again, a lot of data in one graph, and the violin plot is actually a wonderful way to depict data. Thank you very much. Have a nice evening. Yes.
Can't make it to class on Monday. Am I able to take it another day, or am I able to take it from where I am? So I'm not gonna. I think I just.
Okay. Well, you can always come on Zoom. There will be a recording for every class. You will be marked as absent, which is if you miss 1, 2.